Have you ever wondered how the world of electromagnetic fields functions, especially when it interacts with materials? Let's dive into it, starting with the basics. Maxwell's equations in a vacuum. Maxwell's equations are a set of 4 fundamental principles that describe the behavior of electric and magnetic fields in a vacuum. In other words, in a space where there is absolutely no material matter. Firstly, we have Gauss's law for electric fields. This law states that the electric flux through a closed surface is proportional to the enclosed electric charge. Secondly, there is Gauss's law for magnetic fields. This law asserts that magnetic fields do not originate from any source, meaning the magnetic flux through any closed surface will always be zero. Thirdly, there's Faraday's law of induction, which tells us that a changing magnetic field will induce an electric field in its vicinity. Finally, we have Ampere's law with Maxwell's correction. This principle holds that a changing electric field induces a magnetic field, and a steady current will produce a static magnetic field. Now, what happens when these fields interact with a medium, like a piece of glass, air, or water? Well, the equations change slightly to account for the presence of electric polarization and magnetization. These are effects that occur when electromagnetic fields interact with the material's electric charges and magnetic dipoles. Gauss's law for electric fields in a medium states that the electric flux through a closed surface is proportional to the sum of the enclosed electric charge and polarization charge. Gauss's law for magnetic fields remains unchanged, even in a medium. The magnetic fields still don't have sources, so the magnetic flux through any closed surface remains zero. Faraday's law of induction in a medium tells us that a changing magnetic field induces an electric field in the vicinity, just like in a vacuum. However, it also adds that a changing electric polarization will induce an electric field as well. Ampere's law with Maxwell's correction, when in a medium, continues to state that a changing electric field induces a magnetic field, and a steady current produces a static magnetic field. But it also introduces an additional term that arises due to the motion of electric charges and their interaction with the medium. These modified equations, known as the field equations in a medium, are crucial for understanding how electromagnetic fields behave when they interact with matter. They help us comprehend phenomena such as refraction, reflection, and absorption of electromagnetic waves in materials. So to sum it all up, Maxwell's equations describe the behavior of electric and magnetic fields in a vacuum. When these fields interact with a medium, they induce electric polarization and magnetization, which modify the original equations. These modified equations, known as the field equations in a medium, are essential for understanding how electromagnetic fields behave when they interact with matter. So next time you see light refracted in a glass of water or reflected off a mirror, you'll know there's some serious physics going on behind the scenes.